Assalamualaikum and cordial greetings to all esteemed attendees joining us virtually today. I am Amirah Basyarah binti Zainol Abidin, your presenter for this session. Alongside me are my esteemed colleague Ahmad Zulfadli bin Musa and Associate Prof. Dr. Muhammad Nuzaihan Matno, both instrumental researchers in our investigation. Together, we are excited to present our discoveries on the efficacy of conventional fabrication techniques for nanoscale wire synthesis. Although we are connecting remotely, your participation and engagement are highly valued as we share our insight and research. Previously, silicon nanowires were made using complex methods like local oxidation of silicon (LOCOS) and electron beam lithography (EBL). Meanwhile, in this research, it takes a different approach. We focuses on creating a backgated silicon nanowire field effect transistor by using simpler conventional fabrication techniques. The goal is to show that these straightforward methods can be just as effective as the complex one previously used. So the objective of our work is to fabricate the silicon nanowire utilizing the conventional photolithography and inductive coupled plasma reactive ion etching (ICP-RIE) techniques, where the silicon nanowire will act as a transducer positioned between the source and drain components, and it will incorporate with a backgate to enhance the signal generated, as it will impact the subthreshold regime as well. So this is the methodology for our work, which is we are going to start with the device fabrication, and then the conventional photolithography, and then we go through the high power microscopy inspection, and then we will formation of the source, drain and nanowire as a transducer through the process of lithography and RIE, reactive ion etching, and then we're going to the surface characterization using HPM, SEM, AFM and ADX, and then we will expose the backgate using lithography and wet etch, and then we will do the formation for the contact pad of source, drain and the backgate through lithography process, and then we will go through the electrical characterization using Keithley 6487 picometer voltage source and Keithley 2400 source meter. So in the fabrication process, we are using silicon on insulator wafer. The SOI was then cut into the desired size. We are using the standard cleaning procedure using acetone and IPA for 20 minutes to remove the contaminant from the surface of the samples inside an ultrasonic bath, followed by buried oxide etch (BOE) dip to remove the native oxide from the surface. The last step was washing the sample in the deionized water and dried by using a blower to remove the residual water. On top of the silicon of the SOI wafer, the lithography process began with a positive photoresist spin coating via spin coater for 30 seconds at 5000 rpm. Okay, after the mass transfer, the resist was soft baked on the hot plate at 90 degrees Celsius for 90 seconds to enhance the addition of the photoresist to the wafer surface. The source and drain pattern with nanowire in between were transferred to the silicon wafer via mask aligner for 10 seconds through ultraviolet UV light exposure. So the pattern was then developed using approximately 35 seconds of RD6 as a resistant developer and rinsed with the eye water. As you can see, there is an image of the nanowire where we have to verify after the resist trimming to get the nanowire size that we want to. Okay, and then uh, we proceed with the etching process via inductive couple plasma reactive ion etching ICP-RIE for 21 seconds. The remaining photoresist was completely stripped using acetone and rinsed with the DI water to expose the source, drain, and nanowire. And then the last photolithography process, which is similar to the previous process, was done in order to create the backgate exposure of the silicon nanowire field effect transistor. The backgate etching process was conducted to remove the unwanted BOX layer via BOE for 150 seconds. And then the thin film of nickel as an additional layer and a gold as the terminal pad were next deposited on the sample's surface through the thermal evaporator. As a result, we will cover on the electrical and physical characterization as well I mentioned earlier before. So here we can see the surface morphology characterization where there is a fabricated device, and then here is the 50 times magnification in the dark field view, and then and then we can see the 3D profilometer where we are using the scan rate up for upper limit 0.1 and lower limit 16.14. Next, we can see here is the 3D profile of silicon nanowire, and its surface topography was obtained from the atomic force microscope AFM, and then the field effect field emission electron microscope FISEM was employed to characterize the diameter and shape of the fabricated devices, and then the elemental content and purity of the material was validated by using energy dispersive X-ray EDX. So the EDX spectroscopic profile of the nanowire shows the silicon and oxygen peak arise with the table inset indicates the elemental composition where the ratio of silicon to oxygen obtained is 2.64 to 0.48 and achieve around 76.19% and 23.81% from the total percentage weight. So here is the experiment setup used in our research. The setup involved utilizing a 3-point probe method integrated with a semiconductor parameter analyzer, specifically the Keithley 6487 picometer voltage source and the Keithley 2400 source meter. These instruments were paired with specialized probe to facilitate our measurement and analysis. And the 3-point probe configuration allow us to accurately assess and measure the characteristics of our semiconductor materials. Our goal of conducting the analysis of the semiconductor properties and the study was made possible in large part by this configuration, as you can see in the slide here. As you can see here, when there is no gate voltage is applied, the FET will equivalent as a resistor. But when the gate bias exceed the threshold voltage, carriers are induced at the semiconductor oxide interface, resulting in a significant current flow. Therefore, the conductance of the semiconductor channel between the source and the drain regions can be influenced by the potential at the gate electrode. The result shows the trend for influence of VGS on ID and VD when the VGS were varied from negative 1.5 volt to 0.3 volt, Whereas the drain current increase, the drain voltage also increases, indicate that the silicon nanowire field effect transistor has a good p-type behavior. Therefore, this device showed excellent performance during electrical testing, indicating it works well and meet the expected electrical standard. So as a conclusion, our findings highlight the silicon nanowire field effect transistor enormous potential and dependability, particularly in high performance applications like medical diagnosis. Our study is unique because of the creative method we used to develop a backgated silicon nanowire biosensor. We chose a simpler fabrication process instead of the more complicated ones, such as a low-cost and ABL, which are commonly utilized. This method not only demonstrate the practicality of these less complex technique for fabricating silicon nanowires, but it also has a potential to optimize their manufacturing process. So in particular, our work explores how effective these simpler methods might be, especially when it comes to improving biosensor. So that's all from me and my colleagues. Thank you so much.